In today's video and class, we are going to perform an experiment using the Lambert's law to determine the concentration of our indicators, and this happens to be the methyl orange and the methylene blue in the unknown mixture. And I also advise that for a theoretical understanding of the Lambert's law, I will encourage you to watch my video on Lambert's law. And also, this experiment happens to be a continuation of the experiment to determine the wavelength of maximum absorption. So again, for a better understanding of this experiment, I will encourage you to watch my video on determination of wavelength of maximum absorption. So now let us look at the materials that are needed to carry out this experiment. So we have methylene blue of concentration 10 milligrams per liter, methyl orange of concentration 10 milligrams per liter. We have the UVV spectrophotometer, we have the cuvette and the distilled water. So these are basically the materials that we will need to carry out this experiment. And before we start with our test protocol, first of all, what we have to note is that this experiment is in two parts. In the first part, we are going to plot a calibration curve for the methylene blue, and we will use this calibration curve to extrapolate or determine the concentration of the methylene blue in the unknown mixture. And also, for the second part, we will plot a calibration curve for the methyl orange, and we will use the calibration curve to extrapolate the concentration of the methyl orange in the unknown mixture. So let's start with the methylene blue. So 1, set up 6 test tubes for methylene blue as shown in the table below. So these are the tubes. We have 6 test tubes labeled test tube 1, 2, 3, 4, 5, 6. And in test tube 1, we contains 0 ml of the indicator and 5 ml of distilled water. For test tube 2, it contains 1 ml of our methylene blue indicator and 4 ml of distilled water. For test tube 3, it contains 2 ml of our methylene blue and 3 ml of distilled water. For test tube 4, it contains 3 ml of our methylene blue and 2 ml of distilled water. For test tube 5, it contains 4 ml of the methylene blue and 1 ml of the distilled water. And for test tube 6, it contains 5 ml of the methylene blue with 0 ml of distilled water. So when we are done with that, we zero the instrument with distilled water as blank. And what we have to note is that the test tube 1 can be used since it contains only distilled water. So after zeroing the instrument with distilled water, we measure the absorbance of each test tube at 660 nanometer, and this is because 660 nanometer is the wavelength for the maximum absorption of methylene blue. So when we are done with this, we plot the absorbance values obtained against the known concentrations. So before we continue, I would just like us to look at these key points. So first, the wavelength to use here is 660 nanometer because this gives the maximum absorption of the methylene blue in the determination of wavelength of maximum absorption experiment. And also, we are to calculate the new concentration of the indicator in each test tube since we will be plotting the absorbance values against the concentration. So now let us now see the calculations of the new concentrations of the indicator in each test tube. Basically, we are going to use this equation C1V1 equals C2V2, and we make C2 the subject. So the C2, making C2 the subject to give us C1V1 divided by V2. So where our V1 happens to be the volume of the indicator in each test tube in the table, the C2 happens to be the final concentration of indicator in each test tube, and V2 happens to be the final volume of the indicator in each test tube, which is 5 ml. So now let's start with the calculation. So again, our table is here. So for test tube 1, our C2 will be, now we know that the volume of the indicator used was 0 and the initial concentration is 10 milligrams per liter. So if you have to substitute these values into the equation, you will get 0 milligrams per liter. So for the second test tube, so we have 10 milligrams per liter, which is the concentration of our indicator, and the volume of the indicator used is 1 ml divided by 5 ml, which is the final volume. So you get 2.0 milligrams per liter. So for test tube 3, the final concentration will be 4.0 milligrams per liter. For test tube 4, the final concentration will be 6.0 milligrams per liter. For test tube 5, it will be 8.0 milligrams per liter, and for test tube 6, it will be 10.0 milligrams per liter. So these are the various concentrations for each of the test tubes. So now, when we are done with that, we then plot the absorbance values obtained against the calculated concentrations as a calibration curve. So this is just an assumed table of results. So this happens to be the calculated concentration that we just did. So the first test tube, second, third, fourth, fifth, and sixth test tubes with the unknown concentrations over here in milligrams per liter, and this happens to be the absorbance values. And if you see over here, the first test tube is given as 0 because we used it as our blank against the rest of the test tube. So to plot a calibration curve, we just plot the absorbance values on the y-axis against the calculated concentrations on the x-axis to get our calibration curve. And what we have to note is that before we can use this calibration curve to extrapolate or determine the concentration of the methylene blue in our unknown mixture, we will have to look out for the equation of the line using Excel, and the equation of the line for our standard curve for calibration curve is y equals 0.1432s minus 0.031. So where y happens to be the absorbance values obtained, and 0.1432 happens to be the slope, and the s happens to be the concentrations, and the negative 0.031 happens to be our intercepts on the s-axis. So what it means is that if you are to extrapolate or determine the concentration of the methylene blue in the unknown mixture from the methylene blue calibration curve, we first have to note the absorbance value of the methylene blue in the unknown mixture at 660 nanometer, and we know that the absorbance value for the methylene blue in the unknown mixture at the wavelength of 660 nanometer is 0.746 from the experiment that we did to determine the wavelength of maximum absorption. So when we are done with this, we just make as the subject in this equation and put the value of the absorbance obtained as y into this equation over here. So what it means is that if we want to extrapolate or determine the concentration of the methylene blue in the unknown mixture, we'll just make as the subject, and making as the subject will be y, which is 0.743 plus the intercept 0.031, all divided by the slope, which is 0.1432. And if you are to do that, you will get a value of 5.43 milligrams per liter. So what it means is that the concentration of the methylene blue in the unknown mixture is 5.43 milligrams per liter. So once we are done with this, we will just come to the graph and just trace it. So this is 0.746 absorbance over here to the 5.43 concentration on the x-axis as shown over here. So this is how we use the calibration curve to extrapolate or determine the concentration of an unknown compound. So let us now look at the second part of the experiment, which involves the plotting of the methyl orange calibration curve and using the calibration curve to extrapolate or determine the concentration of the methyl orange in the unknown mixture. So first of all, we will have to make a setup for the methyl orange using the table over here. So as you can see, we have our 6 test tubes labeled test tube 1 to 6, and this is the volume of the indicator that is needed and the volume of distilled water to be used. So if you should look at the first test tube, it contains 5 ml of distilled water. Test tube 2 contains 1 ml of the indicator and 4 ml of distilled water. For test tube 3, it contains 2 ml of the indicator and 3 ml of distilled water. For test tube 4, it contains 3 ml of the indicator and 2 ml of distilled water. For test tube 5, it contains 4 ml of the indicator and 1 ml of distilled water. And test tube 6 contains 5 ml of the indicator. So when we are done with it, we will subject each test tube to the same protocol as we did for the methylene blue. But the only difference here is that instead of using the wavelength of 660 nanometer, we will use the wavelength of 460 nanometer. So this is the only difference. So when we are done with it, so this is the assumed table of results for our experiment. So if you should look at the table, so we have our calculated or known concentrations over here for the first test tube to the 6th test tube, and these are the respective absorbance values obtained. And one key thing that we can also see here is that the absorbance value for the first test tube is 0 because we used the first test tube as a blank against the rest of the test tubes. So if you want to plot the calibration curve, we plot the absorbance values on the y-axis against the concentration values on the x-axis as shown here. So after plotting the calibration curve, we will also have to determine the equation of the line, and this happens to be the equation of the line for the calibration curve, which is giving us y equals 0.0839s minus 0.0212. So where y happens to be the absorbance valued, the 0.0839 happens to be the slope, the s each the concentration, and the negative 0.0212 is the intercept on the x-axis. So to determine or to calculate for the methyl orange concentration in the unknown mixture, we will make as the subject in this equation and put the value 0.363 in place of the y, because this is the absorbance value of the methyl orange in the unknown mixture at 460 nanometer. So if you are to do this, we will get our h to be equal to the 0.363 plus 0.0212 all divided by 0.0839. And if you are to solve the equation, we will get a value of 4.58 milligrams per liter. So what it means is that the concentration of the methyl orange in the unknown mixture is giving us 4.58 milligrams per liter. So once we are done with this, You will just trace the absorbance value obtained, which is the 0.363 over here, to cut the calibration curve and extend it to the x-axis to determine the concentration of the methyl orange in the unknown mixture as shown here.